Hello guys, this is Anna once again, and this is our second physiology lecture in the topic. Today's topic is the types and functions of different types of cells and irritability and conduction, which is mainly about the neuronal cells, and we're going to discuss the action potential today, the conduction, and many important stuff. So let me start with the concept, which you already know, that certain types of cells create certain types of tissues in our body. Then these tissues create organs, and some organs together are referred as the organ systems. And before we actually start discussing the functions of the organ systems in our body, of course, we have to know the function of each major type of cell, yeah? So today, let me start with the discussion of the muscle tissue, neuronal tissue, and then certain characteristics of the neuronal cells. Yeah. As for the muscle tissue, well, its major function is contraction, of course, and we have three types of muscle cells, like skeletal, cardiac, and smooth. While the skeletal and the cardiac muscles are both striated, but a smooth muscle is not striated, and smooth muscle and cardiac muscle have one thing in common, that they are not controlled by us directly. They are mostly controlled by the autonomic nervous system, like parasympathetic and sympathetic. For example, the smooth muscle is found in the vessels, in the GI tract. In vessels, I mean that when the smooth muscle is contracted, contracted by the effect of, for example, sympathetic nervous system, then the radius of the vessel decreases, which means the vessel is constricted. This is necessary for increasing the blood pressure in the body. As for the cardiac muscle, also cardiac muscle is not controlled by us directly. Well, the heart has its own pacemaker cells, like symmetrical node, like atrioventricular node. Then the impulses from the pacemaker cells are spread along the the His bundle of His somewhere there at the septum, near the septum. Then to the Purkinje cells, well, then pacemaker cells are located somewhere there, SA node and AV node, and then the His bundle of His, then the Purkinje cells. And afterwards, only afterwards, cardiac muscle cells are activated. Impulses are conducted throughout the whole heart, and conduction of these impulses is facilitated by what's called gap junctions. And since we have a lot of different gap junctions in the cardiac muscle works as a whole big syncytium, which means that impulses are really spread together continuously, and they contract at the same time. Yeah, this is very important for normal function of the heart, normal and coordinated contraction of the heart. But when we have, for some reason, the dilation of certain chamber, for example, the atrium dilation in case of mitral stenosis. Mitral stenosis is, I can explain easily that when there is a mitral stenosis, it means that mitral wall, which is located between the left atrium and the ventricle, is constricted, or in other words, the radius and the diameter of the mitral wall decreases, so that left atrium has to contract really strongly in order to pump blood into the left ventricle. And during this contraction process, which is not so effective, more blood is left in the left atrium, and more blood accumulates inside it. This can lead to dilation of the atrium, and while there is a dilation of the atrium, the gap junctions, which you see here, are damaged. So as I've mentioned, these gap junctions are really important in terms of coordinating contraction of the whole myocardium together. So since my gap junctions are damaged, it can lead to a very life-threatening and very dangerous condition called arrhythmia. And for example, in mitral stenosis, patients often develop arrhythmia called atrial fibrillation, which is absolutely dangerous. It's important for you to understand that gap junction damage can play a part in it. Yeah. As for the skeletal muscle, Here I can show you the picture. Mostly the skeletal muscles are attached to the bone, but also we have certain muscles which are not attached to the bone. The attaching point is called kind of tendon. Afterwards, like there, over there, this, yeah, I'm sure you see my cursor right now. This is the tendon. Then we have the muscle itself, and muscle has several linings. For example, the epimysium lines the muscle outside of it. Is an external surrounding of the muscle. Then we have the perimysium for specific fascicles. These are the fascicles, and fascicles are surrounded by the perimysium. And inside the fascicles, we have muscle fibers, which are surrounded by the endomysium. This is endomysium. So 3 linings: epimysium, perimysium, and endomysium. And what is the function of skeletal muscle contraction, which is controlled directly by us, right? Not sympathetic or parasympathetic nervous system, but or autonomic nervous system, but by us actually. That's why we have a lot of mitochondria inside the muscle fibers, a lot of sarcolemmas. Mitochondria are responsible for producing ATP, for energy production, which is quite important for the skeletal muscle working process, and sarcolemmas contain calcium inside them, and calcium is another important thing for contraction. We're going to study this in our physiology course. And another thing I want to add here is that the muscle fiber is sometimes referred to as a muscle cell, but it's actually not a single cell, but the combination of several different cells. Yeah, and a lot of mitochondria are found here. As for the smooth muscle, I've already mentioned that smooth muscles are found in internal organs, in the vessels, and mostly they are not controlled by us directly, they are controlled by the autonomic nervous system, yeah? As for the nerve tissue, well, in the nerve tissue, we have the neurons, which are responsible for generation. Pay attention to both generation and conduction of the electrical events. We're going to discuss it really in a couple of minutes. And the neural glial cells, which have different types of functions. I'm going to discuss them as well. So let me start with the neuronal, with the neurons, and they have certain parts. For example, the cell body, the dendrites, and axons. As you see on the picture, here is our cell body. It has little short branches, which are called dendrites, and the longer branch, which is called axon. The axon has synaptic terminals, which helps it to connect with the other cells as well. And the neurons are responsible for generating and conducting the action potential, which I'm going to discuss in a minute. Yeah. As for the neuroglia, we have different types of cells like Schwann cells, which are responsible for myelinating cells in the PNS, or in other words, peripheral nervous system, and the oligodendrocytes, which myelinate the CNS or central nervous system neurons, axons, specifically axonal parts of the neurons. Well, one Schwann cell myelinates one axon, whereas one oligodendrocyte can myelinate several different axons of the different neurons. Yeah. As for the microglial cells, they have monocytic origin. They act like macrophages, but they are the residents of the CNS, so they have exact same functions as the macrophages have, like phagocytosis and so on. And as for the ependymal cells, well, ependymal cells are responsible for production and resorption of the cerebrospinal fluid. And finally, the astrocytes have nourishment effects in the CNS. And by the way, they are also the part of the blood-brain barrier, which is an important barrier which doesn't allow certain drugs, certain huge molecules, certain pathogens into the CNS. So blood-brain barrier is kind of a important thing surrounding the whole CNS. Yeah. As for the 2 major functions of the neurons, well, I've mentioned, and I've already mentioned them in the beginning of the presentation. Now I'm going to give you the exact explanation. So the irritability refers to the ability of the neurons, cells of the nervous system, to detect and to respond to certain stimulus, right? And the conductivity refers to the ability of the neurons to transmit signals from one neuron to other neurons, and from a neuron to muscles and glands, and so on and so on. So first we generate an impulse and then we conduct it specifically to other neurons or other parts of the body. So what is irritability? But irritability is sometimes called excitability as well. But before we actually discuss irritability, I want to show you this whole action potential thing and remind you that during rest, we have this kind of name for it, the resting membrane potential. In resting membrane potential, the potential of the cells, mostly all of the cells are negative, and in case of neurons, the resting membrane potential is somewhere -70, -75. In other cells, the resting membrane potential may be -80 then, or even different number. Yeah. So what I mean in resting membrane potential, in this I mean that the potassium, where is the picture? Potassium and sodium pumps, sodium potassium pumps, which use ATP for working properly, maintain this resting membrane potential. Now, so let's see how. A certain amount of sodium, specifically 3 sodium ions and 2 potassium ions are carried by this sodium potassium pump, but important thing here is the direction of those ions. Well, the potassiums are carried into the cell, whereas the sodium leaves the cell. So now imagine when the 2 positive ions enter the cell and 3 positive ions leave the cell, it means that the internal membrane of the cell has to be negatively charged, because we have just 2 positive ions inside the cell and 3 positive ions are leaving the cell. So it's quite logical that the internal part has to be negatively charged, right? And another thing here, which is going to help us to understand this specific detail, is the term called equilibrium potentials. Every charged ion that the cell membrane is permeable attempts to push the resting membrane potential of the cell towards its equilibrium potential. Now, if I tell you that during resting membrane potential, the membrane is mostly permeable to potassium ions, then you have to understand that the potassium will try, here is the equilibrium potential of potassium, will try to push the membrane potential towards its own equilibrium, I mean -80, yeah? But actually during resting membrane potential, I mean in neuron, we don't have resting potential -80. We have somewhere -75 or even -70. Not exactly the same equilibrium potential as the potassium has. Why? Because besides potassium, other ions are also able to move through the membrane. For example, as I've already mentioned, several sodium ions leave the cell via this sodium potassium pump. Yeah, so don't imagine that higher permeability to potassium, highest permeability, I would say, means that only potassium moves through the membrane. No, other ions also move through the membrane, but in a little degree. Yeah, that's why the resting membrane potential is closer to -80, but never equal to -80. It's somewhere -7, -75. Yeah. So now, if we change the permeability of the membrane to another, if we switch the highest permeability of the membrane to another ion, for example, to the sodium, and if we open a lot of different sodium channels in the membrane, so what's going to happen? Sodium will start moving into the cell according to the gradient. Why? Because sodium is even more outside the cell than inside the cell. Yeah, that's why if we open the channels of the sodium according to certain stimulus, then the sodium, according to the gradient, will start entering the cell, and if the permeability to sodium is highest, then it will try to push the membrane potential towards to plus 60. But as you see here, well, I'm actually about now talking about the action potential. Yeah, I'm trying to explain this whole situation. So when the action potential starts, somewhere the sodium channels, voltage gated sodium channels are opened. This means that more sodium enters the cell, and the sodium tries to push the membrane potential towards its equilibrium potential, which is plus 60, but it never becomes plus 60. It becomes closer to this equilibrium potential. For example, plus 35, plus 30, somewhere like this. Different books and different pictures may show different numbers, but it doesn't really matter. Main thing is to understand that from negative charge, we start and go up to some positive charge. And at the maximum point, sodium channels become closed. Yeah, after closing the sodium channels, they turn into what's called inactive state, which means that they are not ready to open because of some another and new signal. So new signal will not be able to turn on a new action potential. Yeah. So what happens next? Next, the potassium channels at this point. Potassium channels open, and according to the gradient, potassium starts leaving the cell. Not entering the cell, but leaving the cell. Why? Because potassium, amount of potassium was higher inside the cell and lower outside the cell. That's why, according to the gradient, once again, I'm repeating, potassium will start leaving the cell. So at first, during depolarization, this phase, upward deflection of the action potential, is called depolarization. And this phase, the downward reflection of the action potential, is called repolarization. So in depolarization, sodium used to enter the cell. So we accumulated positive charge inside the cell, and the action potential became positive. Yeah, as you see here. But in the repolarization phase, the positive charge, I mean potassium, which is positively charged, leaves the cell, which means we again go back to negative numbers. Yeah, and at certain point, the charge will become even more negative than the resting potential used to be. Why? Because once again, potassium permeability to potassium is really increased now, and potassium tries to push the membrane towards its equilibrium potential, minus 80. So at certain point, at this specific area, even the charge of the membrane may even become more negative, like minus 80. And that's why this specific area is called hyperpolarization. Yeah, so we had depolarization there, repolarization over there, and this area is called hyperpolarization. And in hyperpolarization, once again, I'm repeating, the cell is not ready to start a new action potential. None of the signals can turn on the action potential. That's why this is called refractory period. And after this hyperpolarization is over, then we will get back to resting state, to our resting membrane potential. And after getting back to the resting state, the cell will be able to reply to a new signal and start a new action potential. Yeah. So this slide also represents which channels are opened in specific parts of the action potential and what are the directions of the ions specifically, which is really important. And as for the all or none effect, now let me tell you this. When the signal is not so strong, and this is shown on this picture, when the initial signal is weak, and it's not really able to reach a certain threshold, then the action potential is simply not started, not turned on, and this little potential happens there, which has no effect at all. So the main thing is to reach the threshold, and after that, after reaching the threshold, it doesn't really matter how strong the stimulus is. If the stimulus is enough to reach the threshold, then in every single case, even weak, medium-sized, and strong stimulus can produce the exact same action potential with exact same amplitude. So after reaching the threshold, then the amplitude of the action potential is standard. I would call this in this way, and it does not depend the strength of the stimulus itself. Yeah. So as for the refractory period, I've told you that we have refractory periods divided into two parts, two types. These are the absolute refractory period and relative refractory period. Absolute refractory period means that no other signal can turn on another action potential. Doesn't matter whether the signal is strong or weak. And relative refractory period means that some stronger signals can still turn on the action potential, right? Okay. As for the clinical correlation, I told you that triggering mechanism of starting action potential, depolarization, is opening the gated sodium channels. Yeah. So if we just simply block the sodium channels, we will get no action potential development. So no impulses will be conducting along the axons, so from one neuron to another. So no feelings, no sensations will reach the brain actually. Yeah. And why do we need it? We need this principle in the local anesthesia. For example, the cocaine was the first molecule or first thing actually used for this purpose, but it has effect of binding and blocking sodium channels, but then its abusive effect was revealed, so the cocaine was changed by other drugs like lidocaine and so on, which are actually frequently used today. And why do we need this lidocaine and other stuff in local anesthesia before the surgery starts, for example? Because we don't need the patient to feel pain. We don't need the patient to feel touch and pressure during the different procedures, even small procedures, even surgeries, huge surgeries. We want the patient to be relaxed, not to feel the disturbing pain and disturbing pressure and touch. Yeah. So this is really important thing to understand. So now let's move on to the conduction thing. Well, I've already discussed the irritability, the action potential, how the impulse can activate a certain neuron. Now let's see how these impulses actually traveling between the neurons, between the neuron and muscle, and so on and so on. So let me tell you that the neuron has a some cable properties. What I mean in this is shown on this picture. So when the action potential starts on certain at certain point, for example, axon hillock, then these can activate its adjacent region, and next action potential takes place. The first one is still in refractory period. Then it activates the adjacent area, and next action potential develops, and the previous area is in refractory period, and the previous area is already ready for getting a new signal and developing a new action potential. So step by step, one by one, the whole axon can be activated. And the sodium channels can be opened along the whole axon, so the impulse can travel from axon hillock to the end end of the axon, like synaptic terminal, and so on and so on. But now let me tell you this. There is a difference between the myelinated and unmyelinated neurons. Why? Because in myelinated neurons, you know already that the Schwann cells and oligodendrocytes are responsible for myelination. And when the neuron is myelinated, it means that inside the myelin sheet, we don't have any kind of channel, yeah? But between the sheets, we have what's called RNVS nodes, which have a lot of sodium channels inside them. So instead of activating all the parts of the neuron, instead of turning on action potential on every single area of the neuron step by step and one by one, this action potential chain can actually skip certain areas and skip exactly the areas which are myelinated and which do not have the channels. So they skip step by step, and when the action potential starts in, for example, one run-via node, then it jumps into the second run-via node, then into the third run-via node. So myelinated axons conduct the action potential faster than the unmyelinated axons. Why? Because fewer action potentials are produced along a given length of myelinated axons. So unmyelinated one needed to create so many little action potentials step by step, but this one can jump and actually develops fewer potentials faster. That's why long axons, the neurons with the long axons are mostly, not mostly, but generally myelinated, because impulse has to be conducted really quickly. And there are certain types of disorders when so our immune system recognizes myelin sheet as unusual and unknown, and immune system starts attaching it and disrupting it. It's a really bad situation for the neurons, because when the myelin is disrupted, and the long neuron, as you understand, requires this myelin sheet to spread the impulses really quickly from one area of the body to another. In this specific case, when the myelin sheet is disrupted, we get really slow movements, really slow motions, and a lot of disrupted reflexes as well. So I think that's it about the conduction. I would be happy if you understand the major concepts here, and at the end of the presentation you see your homework, the major book, Stewart Fox, 15th edition, 2019, chapter 1, chapter 7, and each parts are indicated. So thanks for listening once again. And in case of questions, you can reach me out anytime you want. So goodbye, guys. See you next time.